In this video, we will discuss composite shear wall design in ETABS. Let's get started. A composite shear wall constructed using steel plates and infill concrete is a structural element typically designed to resist lateral forces in buildings. Each wall segment consists of two steel web plates along its length, with flange or closure plates at the ends as shown in Figure 1-1A. The web plates are interconnected using regularly spaced tie bars arranged in both horizontal and vertical directions, providing sufficient stiffness to the wall before the concrete is poured in. Also, composite beams may be employed to connect one or more wall segments. These beams are also typically constructed as composite sections with steel plates filled with concrete, as illustrated in Figure 1-1B. Okay, let's open up ETABS. Here's the model we'll be using. So shear walls are typically modeled using shell elements, frame elements, or a combination of both. Includes built-in composite wall sections for both shell and frame elements, making the modeling process more efficient. So let's take a look. If we go to Define, Section Properties, Wall Sections, we can take a look at a wall property. You can specify the property type as well as modeling type must be composite. And we can take a look at the property data as well. You can set the concrete material, steel material, as well as property data including length, overall thickness, web plate thickness, flange plate thickness, as well as tie bar diameter. Composite shell section is created. The program internally creates a shell frame section with a single material and an equivalent thickness to match the stiffness of the composite section defined by the user. Shells using the composite wall section are considered as thin shells for the analysis. Let's take a look at a beam. Here, under General Data, you can specify beam spandrel and then use this to be assigned to a shell element. Let's take a look at a small portion of this model we're working on. I want to take a moment to discuss pier and spandrel labels. They are assigned to frame and shell elements to identify all structural elements that make up each wall. The program internally creates the wall and beam elements based on the pier and spandrel definitions. So at each story, all the elements with the same pier label form a single wall, and all the elements with the same spandrel label form a single beam. This figure presents an example of a wall core with an appropriate assignment of pier and spandrel labels. The example has three different walls connected through four coupled beams. There are two C-shaped walls, P1 and P3, on each edge of the core. On the middle, there's an I-shaped wall, P2, connected to both C-shaped walls by the webs. Note how each wall is composed of multiple shear elements that share the same pier label. Similarly, each coupling beam has its own spandrel label assigned. All the labels can span multiple stories so that the wall elements are created at all stories. Okay, let's go ahead and run the analysis and design and take a look at some output. Once the analysis is run, we'll go to Design, Shear Wall Design, Start Design Check. To get more detailed information about the design, we can right-click on any pier or spandrel. Here you can see the ETABS Shear Wall Design report. Here we have information about material properties, wall dimensions, wall section properties, as well as design parameters. Information about all design, including overturning moment, wall stack amplified flexural demand, as well as pier biaxial flexural strength. Cross-sectional analysis for PMM interaction, and here's the diagram here shown below. We can also get information for the spandrel. Information about the coupling beam is shown here.